Okay, so good morning. Welcome to the first keynote. Okay, so it's my great honor to introduce our first keynote speaker, Dr. Asokan. Yeah, so he gave us a talk extraction on complex DNN models, real threat or Boogeyman. And Dr. Asokan is a professor of computer science at the University of Waterloo, where he held David Charlton Chair and also serves as the executive director of the Waterloo Cybersecurity and the Privacy Institute. He is also an adjunct professor at the Aalto University, where he was the founding director of the Helsinki Aalto Institute for Cybersecurity. He was a professor of computer science at Aalto University and also at the University of Helsinki. He also held a very senior positions in industry. Dr. Asokan's primary research theme is system security broadly, including topics like development and the use of novel platform security features, applying cryptographic techniques to design secure protocols for distributed systems, applying machine learning techniques to security privacy problem, and understanding addressing the security privacy of machine learning applications themselves. And he is an ACM fellow and an attribute fellow. So I turn the floor to Dr. Asokan.
I'm going to be talking about extraction of DNN models. This is some work my students have been doing for the last several years. And those of you who were at the in-person event might recall the general talk that I gave about security and privacy concerns in machine learning models in general. And today I'm going to talk about a specific concern, which is model extraction. So my outline of my talk is going to be, first I'll try to tell you a little bit about model confidentiality. That's the subject of today's talk. And try to say why model confidentiality is important. And then the bulk of the talk I will spend on explaining what model extraction is and how feasible model extraction is. And then towards the end of the talk, I'll discuss some ways in which model theft can be countered. And if you have time, I'll talk about the concern of simultaneously deploying defenses against different concerns, not just model extraction, but other concerns as well. So let's start with why is model confidentiality important? So those of you who were there yesterday would have seen me putting up this slide, which says that AI is going to be pervasive, and whatever metric you take, it'll be an exponential growth that's predicted over the next several years. So here in this case, it's market cap. And the market cap means that people see business opportunity, right? So people who spend the effort, expertise, and resources to train machine learning models do so because there is a business advantage for them. They can turn that into a commercial venture. So there is this underlying intellectual property in the machine learning model that gives them this business advantage, and then clearly they are interested in protecting that. But this business advantage comes at certain costs. So first of all, anyone who wants to train a machine learning model has to collect relevant data. That can be a very time-consuming and expensive process. If they're building a classifier, they also need to label the data. So that's much more resource-intensive and a process that requires expertise. Then to decide what kind of model architecture to use, what kind of training configuration to use requires expertise. And finally, there's also resources that are spent on training, the processing power, the memory, the storage, and so on. So this is the context in which one should think about model theft, that when machine learning is so successful and there's such a big business opportunity to attract not only people who want to do legitimate business, but adversaries as well. And an adversary's incentive is if they can get the same benefit as a legitimate model owner without having to pay all of these costs, that's a very compelling case from an adversary point of view. So this is why people in industry who are thinking about deploying models worry about model confidentiality. So what does it mean? stealing a model. The most straightforward way you can think of about stealing a model is what we can say refer to as white box theft. So if I train a model and then you buy it from me, or you subscribe to my model and I give it to you, you have access to the bits and bytes of the model itself. Right? You have physical access to the model, and because you have physical access, you know its structure. You can even examine its internal structure. You can observe what the model does while it's executing on some input and so on. And you can imagine why instances where this would be the case. Perhaps the most widespread instance is if you buy a mobile app, install it on your Android phone, iPhone, and many of them actually incorporate models. And there may be some obfuscation in the model, but otherwise the model is actually there in the application package. Another example might be that various machine learning models that are integrated into devices, like you may have an observation camera that does facial recognition. This camera that's sitting in front of me is trying to figure out where the voice is coming from, where my face is, and it's clearly there's a machine learning model inside. So again, I as a user effectively have physical access to that model. I can take it apart and probe the model and so on. So that's white box theft. And there are different ways one could think about defending against white box theft of a model, right? And this is very popular in the research literature. One way to do that would be to do the model computation on encrypted data. So the model itself, like the model weights, would be encrypted, and the way to do computation for a given input would be effectively turned into the problem of computing with encrypted data. Another potential protection is to use hardware security mechanisms. So I have long worked on trusted execution environments. If you have a smartphone, if you have a tablet, if you're running a cloud server, chances are that your hardware already has hardware security mechanisms built into them. And you can use this to run a model on your device without you having direct physical access to it. So again, this is a technique that's widely used to let customers have access to models without being able, but let customers be able to use models without having physical access. And then the last thing is, of course, put the model in some kind of firewall cloud service. So think about Google Cloud or Google Translate. All of us use Google Translate, but the model sits somewhere in Google's cloud servers, and the access to the customers is given via an API, and the rest of the model is firewalled. So essentially, what all of these techniques are doing is to turn this white box access into black box access, so that the users, legitimate users, no longer have physical access, and they interact with the model via a well-defined interface, which we can call the prediction API. And this can be a direct API, so in the case of, say, Google Translation or image classification and so on, or it can be indirect. Maybe when you go to Netflix, it recommends you the movies that you might be interested in. You don't have a direct API, but indirectly underneath there is a model that's looking at your past history and trying to recommend movies that you might be interested in. So I've told you like different ways in which white box access can be prevented. And essentially that's sort of turning the access to a black box nature. So someone could ask the question, is this enough to prevent model theft? And the answer is no. And this is where model extraction comes in. So we'll delve a little bit deeper into that. So the setting, remember, is that there is a model. The model is not accessible to the client directly. There is some kind of firewall, maybe a cloud firewall, maybe hardware security, maybe encryption. But the client is sort of forced to interact with the model via this well-defined API. But as you can imagine, the API essentially makes the model act like an oracle. Every time you send a query and get a response, you learn some information about the model, right? So our adversary model is that the client, will give you access to your model via an API to all your legitimate subscribers, but one of the subscribers or one of the clients is potentially malicious. And the goal of this client is to ask queries via this prediction API, which is allowed to do legitimately, and use that information to build another model, which we can call the surrogate model. In the literature, people call it the student model or imitation model. But the intent of the adversary is that the surrogate model is, by some definition, comparable to the victim model. And the only access that the client has is really via this prediction API. So it can send inputs and see model outputs. So already 6-7 years ago, there had been papers that said such an adversary could actually build a surrogate model that is comparable in the utility, in sort of prediction performance to the victim model. And the initial papers dealt with very simple models like logistic regression or decision trees or simple neural networks. And the assumption always was that the adversary has doesn't have access to a lot of data, a lot of natural real data, and therefore the adversary has to sort of make synthetic queries. And it was thought that this is reasonable because if an adversary has lots of data that's needed to build a model, maybe they have solved half the problem and they may not be incentivized into trying to do model extraction. Nevertheless, the original papers took this kind of an adversary model that the adversary doesn't have enough data and that the adversary is forced to generate synthetic data to be able to carry out the model extraction attack. So this is sort of when my students became interested. So about 4 years ago, we showed that one could do model extraction against deep neural networks, fairly simple data sets, and deep neural networks built from fairly simple data sets, but nevertheless more than very simple models. And we followed the adversary model that was sort of assumed to be standard in the literature at that time. So the adversary knows something about the model, not the actual model weights and so on, but the general task and the general structure of the model. And we also assume that the adversary doesn't have a lot of natural data. So if the adversary is trying to steal a model, let's say for X-ray diagnosis based on X-ray images, we assume that the adversary might have like a few X-ray samples, but not a lot of them. And then the adversary uses these natural samples, but also generates lots of artificial data, uses them to query the model via the API, and is able to produce a surrogate model that has comparable accuracy. So we showed that we published this in 3 years ago. In addition to the model extraction technique itself, we also showed that with this kind of an adversary model in mind, we could actually have a simple defense, a detector that can distinguish between queries that come from legitimate clients, because legitimate clients, if I have a medical diagnosis model where the input are X-ray images, my legitimate clients are going to be doctors and physicians and medical professionals, and they're going to query using actual X-rays. Whereas our adversary model assumes that the adversary who wants to steal a model doesn't have a lot of this data, and therefore they are going to also have artificially created samples. And we could exploit this fact to have a simple defense that distinguishes between these benign queries and adversarial queries. So I work a lot with industry, and when we had this solution, we went to our industry partners and said, look, this is a concern. We showed that even deep neural network can be extracted, and here is a defense. And the questions they asked were, they're not interested in simple models built from, say, MNIST or even ImageNet. They want to know whether realistic, complex deep neural networks can be extracted. And the second question they ask is, of course, if that's a real threat, then how can we protect against that? Are the current defenses effective? Are the defenses and the attacks based on realistic adversary models? So at that time, there was a paper from some people in Germany, which was published in CVPR, which is called knockoff nets. And that's an interesting paper, and it's sort of a landmark paper at that time, because it showed that, it answered these questions. It showed that complex models can be stolen, but also it made adversary assumptions which are different from what was common until then in some respects. So one of the assumptions was that they assumed a very capable adversary, a very weak assumptions about the adversary, which makes the attack very strong. Right? So they assume that the attacker doesn't know, doesn't have any training or test data, doesn't have, of course, doesn't know the model internals, but doesn't even know the model semantics. Right? So you might have a medical diagnosis model that is supposed to analyze X-rays and then decide whether the patient has some disease or not. I, as an attacker, don't even know that. I just know that this is some image classification model. And that's a very weak assumption. And therefore, if they can show, as they have done, that it's possible to extract this model, that's indeed a strong attacker. So the color coding here is that the assumptions in red are, they reduce the capability, they minimize assuming capabilities from the attacker. Right? So correspondingly, this means that the attack is very strong. On the other hand, the ones in green are, they make sort of generous assumptions about what the adversary knows. So one such assumption is that they assume that the adversary gets the full prediction probability vector from the query API. So think about a classification problem like digit recognition. There are 10 different classes, right? 0 to 9. And usually when you send an image, let's say an image of a digit 6, you could imagine sort of two kinds of outputs. One output might be that it gives you a full probability vector that says this image is, with 80% probability is 6, with 20% probability or 15% probability of 5, and so on. And this is what they assume. They assume that the models that the attacker is trying to extract give the full prediction probability vector. But quite often, this is not the case in practice. In practice, it might be that you only get one answer. You just say, you give an image and you get back the answer that this is a 6. You don't know anything about what other classes might have been likely possible. Sometimes you get top K. So instead of getting the full probability vector, you might get the top 3 or top 5. Right? So that's, they made a strong assumption about the API. They also assume that the attacker has enough natural samples, but not necessarily from the same domain. So again, going back to the example of diagnosing from X-ray images, they assume that the attacker has lots and lots of images of cats and dogs and whatever. Not necessarily X-ray images, but images, right? So this is different from what previous papers had assumed. Previous papers had assumed that the attacker doesn't have enough data and has to generate synthetic data. Now they assume that the attacker has natural samples, but not necessarily from the same domain. And the last assumption, which is also a generous assumption, but I think is realistic, is that they assume that the victim built their model starting from a pre-trained model, and the attacker has access to the same pre-trained model. And this is reasonable because nowadays nobody starts from scratch when they want to build a model for deployment in practice, right? So if you're building an image classification model for, let's say, X-ray image classification, you would start from a model that's built from a data set like ImageNet. And ImageNet is full of pictures like dogs, cats, whatever. And then they would use the X-ray data to further train that model, to sort of refine that model. And the reason why this works is that in image classification, quite a lot of the initial tasks are independent of what the images are about, right? So they may have to do edge detection, they may have to do some kind of clustering and so on. And the initial layers of a neural network doing these kinds of tasks would look the same regardless of what kind of images that you are trying to train. Another example of pre-trained model is in language models, right? So there are models like BERT and so on that are trained on like really huge language corpus. And therefore they learn a lot about the basic structure of the language, the grammar, and so on. And then for your particular application, you can start from one of these generic models like GPT-2 or BERT or GPT-3, and then specialize it. So if this is what victims are doing, then it's reasonable to assume that the attacker has access to this kind of pre-trained model as well. So we looked at this paper and we thought, okay, we want to first reproduce this because this is a very, very compelling and a sort of a step advance in the state of the art. But we also wanted to revisit their adversary model assumptions and see, have they made reasonable assumptions? What if we try to sort of tweak the assumption, either make it stronger or weaker? So if you are interested, you can look at this paper. So throughout, I give links to the papers that I'm talking about. These slides are on my webpage. So if you Google for my name, you'll find my webpage, and these slides are right at the top of my talks page. The papers that are marked in blue are work done by my students. So in this case, the analysis of knockoff and then revisiting the adversarial model, they are in this paper that was published at AAAI EDSML 2 years ago. And so I'm not going to go through the details, but I'll just give you a summary of what our conclusions were. So first of all, we did reproduce their knockoff nets attack and confirm that with their adversary model, their claims were correct. But then we started sort of revisiting the assumptions. So here's a summary of sort of what happens if the assumptions change. So first of all, they assume that the attacker knows doesn't know anything about the victim model, not even the task, and certainly not the architecture, and certainly not the weights. But in all the experiments, they use the same architecture for the surrogate model and the victim model. And we confirmed that if they are the same, the attack is quite successful. But if they're different, then the attack effectiveness goes down. And you can imagine that even though there is not much entropy in the structure of a model, like what are the layers, how many layers, and so on, there is still some uncertainty. And if the attacker doesn't know exactly what model the victim is using, then the effectiveness of the model steering attack is, it's not destroyed, but it is lowered. But more importantly, if the prediction API has reduced granularity, so that if you don't get the full API, full vector, but you get only the top one or top k, then the effectiveness of the attack also reduced fairly drastically. On the other hand, given their adversary model, so remember that the adversary model is that the attacker doesn't know anything about the model task. They have lots of natural data, but the data is not drawn from the same distribution as the victim model. With that adversary model assumption, we can again have a simple defense, which tries to separate queries that are in distribution. So if I have an X-ray diagnosis model, then I can see if an incoming query is an X-ray image or some other image. And if it's an X-ray image, then chances are that it comes from a legitimate user. If it's some other image, chances are that it comes from an attacker, given the attack model that the attacker doesn't know what the task is, doesn't have access to in-distribution data, but has lots of natural data. On the other hand, you could ask, is this a reasonable assumption, right? So, you can go to Google today and download hundreds of thousands of X-ray images. So there are very few problem settings where the in-distribution data is hard to come by. Pretty much any task that you can think of, the adversary will be able to get enough natural in-distribution data. The only thing they won't have is the data won't be labeled, right? So I'll have lots of X-rays, but I don't know which X-rays correspond to the presence of a disease and which X-rays correspond to absence of a disease if I don't have medical expertise. And so this is something that came clearly when we were discussing with our industry partners, that assuming that the attacker doesn't have access to in-distribution data is a very strong assumption that only applies to some use cases. But for the vast majority of use cases, you have to assume that the adversary has enough in-distribution data. The only thing they don't have are labels. And if you assume such an attacker, then the simple defense no longer works, because then a legitimate user to my model, doctors and medical professionals are going to ask questions with X-ray images, but then so will an attacker. And I won't be able to tell which is a attacker and which is a legitimate user. And of course, you remember that any defense should not harm the utility for legitimate users, right? So if I start throttling people who send lots of queries, it may be that I'm harming some legitimate user who happens to ask a lot of things. So this is why any defense that's based on separating legitimate users from a potential attacker who's trying to extract a model should do this differentiation very effectively. Otherwise, I'm going to be antagonizing my legitimate users. So far I've talked about image classification models, and pretty much as is common with machine learning, a lot of the research papers also use image classification. But there have been papers that show that model extraction is not just a threat for image classification. So I'll give a couple of quick examples. There had been papers that showed natural language processing models can be stolen. One of them, this last one, actually was able to extract Google Translate. They didn't use it, they didn't make the extracted model available, but they used it to find an adversarial example, again, Google Translate. And I'll show you this adversarial example. You don't have to know German to see what the adversarial example is. This sentence is translated in German like this, but then if you change the temperature figure to 102 degrees Fahrenheit, for some reason it translates it to 23 degrees centigrade. This no longer works. It did work for more than a year after the paper was published, but if you go to this link, you will see that it does it correctly now. One more quick example of models that are being stolen are image translation models. So image translation models are where you give an image and then you get another image with some transformation. And I'm sure you have seen examples like this, like for example, FaceApp will take a model and change the gender or change the age. Or there are other image translation models that take, say, a photograph and then turn it into a painting in the style of some famous painter. And so there are mobile apps and there are services that do this kind of thing. So my student extracted this model. You can find the paper in archive. So here is the original image that's input to the model, which is a photograph. And then the output is supposed to be painting in the style of Monet. And one of these is the victim model. One of these is Sebastian Schiller, my student's stolen model. And maybe you can stare at it for like 2 seconds to see which is the victim and which is the stolen model. Well, the point is that it's hard to tell. Both of them seem to do a good job. And it so happens that the second column is the victim and the last column is the stolen model. Similarly, so it's not just translation. There are also super resolution models where you take an image and then refine it so that it becomes sharper. So again, one of these is the victim, the other one is the stolen model, and they effectively perform the same way. So I hope that I have convinced you that model confidentiality is important and that model can be extracted via the APIs. If you assume a powerful but realistic adversary, I hope you have convinced you that they can extract complex real-life models. And then again, in a reasonable powerful adversary model, detecting such an adversary may not be feasible. So how am I doing for time? I have a couple of other things, but I don't need to necessarily go on that. So Professor Lin, how much
we still have around like 22 minutes, so we still have a lot of times, yeah.
Okay, so then I'll go through the rest of the presentation as it is. Okay, so having done this, and feel free to ask me questions anytime. So I'll put the question answer somewhere so that I can see it, or maybe if you want to ask questions, someone can relay the questions to me even if I can't see them. So feel free to interrupt me at any time and ask questions. Okay, so having hopefully convinced you that model extraction is a real problem, let's talk briefly about what can be done to counter model theft. So one could think about, so I already sort of gave you a hint that detection of a model in a strong but reasonable adversary model, or detection of model theft or model extraction is going to be impossible. If we can make restrictive assumptions about the adversary capability, then yes, like for example, differentiating between the queries that come from legitimate users and queries that come from potential model extractor is possible. But that may not be realistic in most settings. In most settings, if we assume that the adversary has the same kind of data like that victims might be querying the model with, then we are not going to be able to detect them. One possibility is detecting, but I just explained that that's not realistic in all cases. The other possibility is, of course, prevent the model extraction or at least slow it down. So there have been papers that talk about this. There's a recent paper that tries to use proof of work. And personally, I think that this is nonsense. Proof of work comes with other burdens. So if you are really deploying a model, it's not realistic to make your clients do proof of work. But I think the basic idea there is if you can increase the cost of people asking queries from your model so that the effect is not too much on legitimate clients, but it'll impose a substantially greater cost on potential model extractors, that could be a way to prevent model extraction, right? So they were using proof of work, but you can imagine it's not proof of work, but it's charging for each query. So quite often in models that are deployed today, the business model is that you get either free access or you get 100,000 free queries. And after that, you pay like $10 and you get another 100,000 free queries. It doesn't have to be like that, right? So it probably has to be like that if you are offering a model for, say, Google Translate or image classification or face translation. But there, you can imagine business cases or settings where you can have pricing that actually helps with model extraction. So again, go back to my example of medical diagnosis based on X-ray images. It would be reasonable to say each query to such a model costs $2 or $5 or whatever, right? So, my provider back home in Waterloo will charge me $5 to actually access the image after I go do an X-ray. And that's considered to be acceptable. And that will not impose a cost on legitimate users. But if a model extractor has to ask 50,000 queries, that quickly shoots up the cost. So increasing the cost to the attacker could be one such defense mechanism, but it may not be always possible. It may be possible in the case of sort of high-value settings like X-ray images, but you can imagine that if I have a autonomous driving case where I have to classify tens of thousands of images every few minutes in order to be able to drive effectively, you can't impose a significant cost on each query. So if you can't effectively prevent or detect, what else can you do? So one possibility is to deter, deploy a deterrence mechanism that removes the incentive for the attacker to try to steal the model. And so this then depends on what is the motivation for the attacker to steal the model. So usually there are two motivations why somebody wants to steal your model. One is, of course, they want to gain from that business advantage that you have from your model, right? So maybe you want to steal Google Translate because you don't want to see ads that Google shows you. Or maybe you want to sell it to somebody else at half the price that the original model owner asks, right? So that's sort of one case. And there the goal of the adversary is really steal the model and then make a business out of that. There can be other reasons why somebody steals a model, right? You may be stealing a model that just you keep it for your own use, or you may be stealing a model and then find a way to evade the stolen model and then hope that the same approach of evading the stolen model also applies or transfers to the original model. So if you limit this to this case that the adversary is stealing a model because they want to undercut your business, then one way to deter that kind of an adversary is to have a technique for ownership demonstration. So if Ali deploys a model, which he has spent a lot of effort and money to build, and I buy legitimate access and then use it to steal his model, and I try to undercut his business by deploying my model and selling it at half the cost, my incentive to do that will be diminished if he has a way to show to an external judge or somebody else that the model that I'm selling is actually stolen from his model. So that's called ownership demonstration. And there are different ways of doing ownership demonstration. The most obvious and the initial papers are dealt with this approach of watermarking, where you add something to the model. So Ali will add something to the model while he's training. And then if he discovers my model and thinks that it's stolen from his model, he'll be able to show that his watermark is present in my model. The second approach is fingerprinting, where you don't add anything, but you try to extract some kind of inherent markers from the model, like fingerprints. And again, if the model is stolen and the fingerprints are such that they survive model extraction, then he'll be able to show that the stolen model has the fingerprints that he claims are his. So the early model extraction, the watermarking papers appeared like a few years ago. And essentially, I'm not going to go through the details, but the basic idea is that the trainer, the person who is training the model has the data. And before they train the model, they add some watermarks, some additional data that constitutes the watermark, and then train the model with the watermark data in addition to the actual training data. And then later, when there's a suspect model, they'll be able to show that it's their model by showing the presence of the watermark. So there are a couple of problems with this approach of watermarking a model in order to demonstrate ownership. The first one is that it only protects against physical theft of the model, because remember what I said before, that the assumption is that the owner of the model adds some watermark to the model and then trains the model. That's not the case with model extraction, right? So model extraction, the attacker asks some queries, gets the responses, and it's the attacker who is going to train the model. The attacker is not going to oblige by integrating whatever watermarks that you want to add to the training data. So that's one problem. Model extraction doesn't really help. Watermarking doesn't really help with model extraction. The second problem, and this is my colleagues at Waterloo and their students showed that many of these watermarking techniques are such that the watermarks can be removed by doing post-processing. So by doing things like fine-tuning and other kinds of refinement, they can remove the watermark, which is what an adversary would do. So I'll briefly talk about this problem of can we do watermarking so that it doesn't only protect white box theft, but it also protects against model extraction. And remember, the problem is that in model extraction, it's the adversary who is training the model. The adversary just asks queries from our model, and we don't have the luxury of having like an extra watermark set that we can add to the training data. So the only thing we can do is essentially the adversary is choosing the training data. They're asking questions from our model, and that's what they're going to train. So the only leeway we have is to take some of the data that the adversary has chosen and then turn that into a watermark. And there we have to be careful, because if we sort of interfere too much with the adversary's data and watermark them, that might harm the utility for legitimate users who query our model. Because when someone queries our model, we don't know if they are potential attackers or legitimate paying customers. So essentially, the idea we did in a paper that we published last year in ACM Multimedia is for a very small set of queries, we are going to return incorrect predictions, right? And this has to be very small so that we don't harm the utility for legitimate users. And what we show is that with minimal loss of utility, something in the range of like less than 0.5%, we can embed watermarks that would be in the model that's trained by the attacker, because we are going to flip the predictions in some of the queries, and the attacker doesn't know where we flip the predictions, and they are going to train a model with that. So again, if you're interested in details, you can ask me questions later or look at the paper, but I just want to give you like a general idea. There are sort of different, so whenever you have a defense like this, a deterrence mechanism, you have to argue that it is robust, right? And an attacker who knows that this is your defense wouldn't be able to evade that. So in the paper, we discuss different ways in which the attacker can evade this. For example, double stealing, right? So the attacker can steal our model via model extraction, build the model, and then steal it again. And if they can do that without the accuracy of the model dropping too much, they would have succeeded because in the second stealing, there is no watermarking at the prediction interface. The second, and maybe the harder problem is, how do you decide which queries you're going to watermark? If you choose it randomly, then the attacker can easily evade that, because what they will do is they'll send two queries that are very close to each other. And if we decide that one of them is watermarked, the other one is not, then the two predictions that are returned are going to be different. And the attacker can just throw those two things away, right? If there are two similar queries, very, very close to each other, and the predictions are different, they're going to throw them away because the chances are that one of them is watermarked. So we have to have a mapping function that somehow groups similar queries together. And if you're dealing with, say, images, what does similar query mean? We really have to have a way of capturing perception, right? So two images that are perceived to be similar by a user would be classified the same way. So in the paper, we discussed the challenges in doing this. But if I have to summarize this in a way, I think our paper shows that it is possible to watermark in a way that would survive model extraction, but it comes with certain caveats, right, about the difficulty of making those solutions in all cases. So I want to just briefly talk about fingerprinting, and fingerprinting became sort of popular in the last couple of years in response to this concern that watermarking is sort of adding something to the model. And whenever you add something to the model, you could do the adversary could do post-processing to remove those, whatever you added, and that way get rid of the watermark. But if you don't add anything to the model, if you try to extract something inherent about the model and use that as the ownership verification mechanism, then the attacker won't be able to remove it, right? Because it's something inherent to the model. So there have been a number of proposals recently. The first one is, it's actually not model watermarking, but data watermarking. This is a proposal from Facebook, where they would be able to show if you build a model using a data set, they'll be able to sort of work back which data set it was built from. My colleagues at Waterloo had a paper called Controllable Adversarial Examples, where they try to differentiate between adversarial examples that transfer between a parent model and a child model, and use that as a way to sort of fingerprint a model. And then the last one is people from Toronto had a proposal called dataset inference, which is essentially a way to, given a model, the model owner knows the original full dataset, and therefore they'll be able to devise a method to do what they call dataset inference, to show that the model was built with this particular dataset. And so all of these are potential fingerprinting solutions. All of them come with certain caveats. And I'll briefly talk about this. So dataset inference is perhaps the best of these. But in our experiments, we saw that it is susceptible to false positive, meaning that if say, Ali deploys dataset inference for his model, and I have a model that I built from a completely independent data set, but drawn from the same distribution, his dataset inference against my model would succeed. Therefore, he will falsely accuse me of stealing his model, even though I didn't steal his model. So that's a false positive. And we saw that there is a possibility of false positive in their technique if the dataset that Ali used and the dataset that I used, they are different, but they are drawn from the same distribution. So in the remaining time, I wanted to sort of raise a concern that I think is very important, but hasn't really received enough attention. And this is the concern of deploying multiple protection mechanisms, or protection mechanisms against multiple concerns. So many machine learning security researchers, and it has been a very popular research topic for the last decade or so, many popular researchers working in this area concerns themselves with sort of one problem at a time. So all the papers that I showed so far, they're concerned with model extraction or model ownership verification, and that's all they look at. And there are other people who care about privacy, and they work on differential privacy. There are other people who care about evasion, or what's known as adversarial attacks, which I think is a nonsense name because all attacks are adversarial. There are no benign attacks. So, but adversarial examples is a way to evade the models. people who work on that only talk about that problem. But imagine that you are a company like Google or Facebook or Intel, and you want to build a model and deploy that. You're not interested in just one concern. You want your model to be protected against model extraction. You want your model to be protected against any kind of data set inference attacks, or you want to deploy, say, differential privacy. You don't want your model to be evaded, so you want to deploy multiple different techniques at the same time. And we have been worrying about model ownership, but here are a couple of other concerns that need to be defended against at the same time. And then these are just two examples. There are many, many other examples. Right? So we looked around and saw that this interaction between defenses is undisturbed. So there is an ongoing work which is currently under submission where my student looked at 3 different ownership verification techniques: model watermarking, data watermarking, and fingerprinting, data set inference as a fingerprinting technique. And each of them has been shown to be effective by itself. But if you then combine that with one other protection mechanism, like we looked at differential privacy and adversarial training, we wanted to see what happens. So here are the 5 techniques that we looked at. The first 3 are ownership verification techniques. The 4th one is a technique to defend against evasion or so-called adversarial attack, against inference. So it's differential privacy. And the last one is adversarial training, which is supposed to defend against these so-called adversarial attacks. And our baseline is that each of these techniques has a metric, accuracy or whatever particular protection mechanism. And what I tried to show here is that each of them deployed by itself does very well. Right? So it does adequately. So again, I will not show the details. You can go to this paper to look at the details. But when we combine 2 methods, we decide that 2 methods are in conflict if any of the 3 metrics, either the accuracy or the metric for the first defense or the metric for the second defense, if any of these fall below, drop below a certain, above a certain threshold, right? So by the combination causes an unacceptable drop in any of them, then we declare that as being in conflict. So, and here's a summary. So we have watermarking, model watermarking, radioactive data is data watermarking, data set inference is a fingerprinting technique. We look at these 3 with differential privacy and adversarial training, and we look at 3 different data sets in each case. And if it's green, it means that there is no conflict. All 3 metrics are fine. And if it's red, it means that some metric fell short. And you can see that data set inference is doing fine, with the caveat what I told you before, that data set inference, even though it doesn't seem to conflict with anything, it has this false positive problem. But the other things like watermarking, if you combine it with the differential privacy, then watermarking effectiveness suffers. If you combine it with adversarial training, then the adversarial training effectiveness suffers. Right? So we are just scratching the tip of the iceberg. And here is a table that shows like different concerns that one should worry about. And we looked at like a small segment. And in the literature, there are some other cases that have been discussed, not directly as a conflict, but as part of the evaluation. But there's this huge space with question marks. So people haven't looked at what it means to deploy 2 defenses together. And the problem is even worse, right? You're not going to deploy just 2 defenses together. You probably want to deploy 3 or 5 defenses together. And that's going to lead to a combinatorial explosion even to analyze. But then once you find a conflict, you have to then think about how do you mitigate that conflict. Maybe you have to sort of do a trade-off. So in a way, this is like a call for action. So if for those of you who are interested in security and privacy and machine learning, I think there are multiple PhD theses here for people who want to explore this problem. So this is where I will stop. I hope I have convinced you that model confidentiality is important and that models can be extracted via prediction APIs. And using cryptography, you're using hardware security is insufficient for this reason, because you have to give an API to your legitimate users. And once you give an API to the legitimate users, if one of them is malicious, then they can use it to extract the model. There are different kinds of defenses that have been proposed. Deterrence is perhaps the most promising, but all of them come with caveats. And then the last concern is that it takes a lot of effort to study one such defense, but in practice, you need to be able to deploy multiple defenses. So I'll leave a link here where you can see other papers that we have done related to model extraction. I'll be happy to answer questions. Let me see if I have a way of looking at the questions. While you're doing that, I'll also put a little bit of a commercial advertisement here. So if this kinds of work interests you, I'm always looking for postdocs, PhD students as well, but more importantly, postdocs. So if any of you are interested in doing postdoc with us, here is a link and you can reach out to me.